Hello everybody, my name is Craig Bennett and I'm the founder and owner of TechReviews, and today we are going to talk about orbital mechanics, and we're going to talk about Lagrange points, or depending on how you pronounce that, Lagrange points. And we're going to talk about the difference between Newton's version of Kepler's third law and Kepler's version. Now, before we get into this video is pretty much going to be unscripted. And this means that if I mispronounce anything or whatnot, then forgive me ahead of time. It's just easier for me to make it unscripted, and that way I can get a video out quicker and better. I felt that the unscripted videos were actually better than the scripted ones, amazingly enough. But as far as things goes, if you don't like it, then just let me know. But another thing I want to mention is I got into two or three emails asking why do I not talk more about the mathematical formulas, and the reason is I'm assuming that you're coming to these videos for two reasons. First is a refresher. You either work in this field or about to work in this field, or you're studying for this field and you just need a little refresher. And the second is you're a hobbyist. You're just learning this on your spare time and whatnot. Maybe you're developing a game and whatnot. But either case, the simple fact is a lot of these equations take a long time to find the answer. And the reason why that's important to note is, unlike high school and some college math classes and whatnot, where they expect you to spend between 5 and 3 hours, 5 minutes and 3 hours, some of these formulas can take around over a couple days, a couple weeks, to even several months. I've yet to see one that takes over several years, maybe to find the variables, but not the actual doing the math. But when I was in school, one of my teachers that had several doctorate degrees in aerospace, they mentioned that for their thesis, for their last doctorates, they did, I forgot what the mathematical formula was, but it was on space science. And it took them over 12 days, 40 hours, or not 40 hours, but 40 hours a week going at. So that's pretty bad. That's a lot of math. So that's basically going every day to work and working at a really good job, but going every day to work and doing mathematical formulas non-stop. That's pretty bad as far as how bad some of these. And I've heard of some people even going up to 6 months trying to find a conclusion to an equation, because how difficult it is to do some of these and how lengthy it is to do some of these. So as far as this, let's get into the difference between Kepler's version of his third law and Newton's. Now, as far as this goes, we're starting with Kepler's version, and what it pretty much states is a big object, a big mass object with a relevant size, is dealing with little objects with a little mass with relevant size. And what I mean by relevant size is the more mass you have in a single point, the more gravity there is. So you can say something like the size of Earth, but if it has so much mass, the mass of a sun, the entire sun, and the size of Earth, the planet that's the size of Earth that has the same mass as the sun, is going to affect the sun. So it takes both the size and the density of the object. So anyways, as far as things goes, it works really well for satellites, what we see every day with planets and whatnot. It's very nice. It's very nice to deal with that. And it's kind of understanding why Kepler didn't think about binary systems or things with equal or just about equal size, like binary star systems and whatnot. And the reason why Kepler thought of this mathematical formula, which I should show somewhere on the screen right now, and how it only deals with a system like our own, is the simple fact is he was looking at day-to-day life. He was looking at through telescopes and whatnot and figuring out this stuff. He was not taking the actual math, the physics, and the logic behind the physics. It just wasn't really around in his time, and they didn't have high-power telescopes like they do now, so he couldn't see binary star systems and whatnot. So that's something to keep in mind. And his is basically taking things that you can see and making laws around them to make them work. What Newton did, he actually took Kepler's laws and expanded behind it, and said Newton's laws work perfectly fine for our type of system, but what happens if you got multiple stars or planets orbiting around planets or things like that? Well, then you have a different set of... And before I get into these rules, one thing I want to mention, the relevant line, basically it shows what everything is orbiting around, which is very important for a second. And like this is a binary star system. There's really an Alpha Centauri C, which is the closest solar system as us, but I only have up is the Alpha Centauri A, Alpha Centauri B, in order to show you a binary system and show you what Newton was going for. Let's turn on the relevant, and as you see here, this is why it's important, because they don't have a sun, they don't have something in the middle that they're orbiting. They're orbiting a center point with nothing there. And basically what's happening, and let's play this for a little while. What's happening is one star is orbiting the other star is orbiting the first star. And to basically put it, one could be little m, the other one could be big M. It doesn't matter, and you may notice from the mathematical formula that I should have up on the screen, there's a little m and big M, and that's what it actually implies, is one star or planet or whatever it may be is little m and the other one is big M. And one thing that you should be noticing now is now we have a bigger circle and a little circle. This means that you actually have one star, planet, whatever it may be, that's a little bit bigger than the other, and obviously not enough to create where this one's orbiting around this, but and this one's not. But as far as this goes, it shows that one is slightly bigger than the other, so it has a bigger orbit. It's very important to note that. And let's actually go and target one of these and show you what happens when we actually have a third. And this is very important. Just stick this pretty far out. And let's play this. So as you can see here, this starts taking effect of that. I have no idea where this is going. Probably taking effect of this. Maybe I got them far enough where it actually works out. This would be kind of cool. And this is one thing that happens in simulations. You don't know if what you have is going to work out or not. And as you see here, this one's starting to pick up on this. That's why I got these lines on. And this one's being thrown out. So I guess it won't work after all. I don't know, maybe. But as far as things goes, there's chaos theory, so there is a chance that anything can go. And you see that they just slingshot around each other. I don't know, maybe it will work. Last time I did this, the two stars shot off from each other and one was stuck in the middle. And that's quite interesting. So anyways, that's very important as far as the understanding the laws. Is Newton's basically deals with when you have two bodies that pretty much weighs equally or very close to equal, and that way you got to count for the actual mass between the bodies, and in this case 3 bodies. So that's also important to note that you can use Newton's law for multiple bodies, and this also deals with in-body problems, so I will be getting to that shortly in another video. And by the way, eventually it gets to a point where you have this going on, which is actually kind of cool, but it doesn't really do that well with this system. So let's get into Lagrange points. Now, as far as this goes, let's put on this and turn on the Lagrange points. With Lagrange points, this could be represented as the Earth and Sun, Jupiter and Sun, Jupiter and moons, and whatnot. But each orbiting body has a Lagrange point. As far as orbiting body, I mean some type of central mass in a orbiting body out here. And this includes orbiting bodies like, as you saw, where there is nothing in between, and you have Lagrange points. The only difference between these, given that you're dealing with a tube body and whatnot, since the Lagrange points pretty much looks at the relation in the middle being a relation, and say the previous thing that we looked at had the Earth here and the Moon here, each thing that's connected to a Lagrange point means an extra set of 5 Lagrange points. So that's important to note. Now, as far as Lagrange points, you have L1 or Lagrange point 1, L2, L3, L4, L5. Very simplistic. Let's actually turn on this so you can see. Now, as far as the L1's always between whatever the central body is, or the central of the relevant point, and the object that you're dealing with. And the L2 is always behind that body. L3 is always behind the central body. Basically, all these points are always somewhere at these positions. Of course, they move along with everything, so let's speed this up. And as you see here, it moves along with the orbit. But as far as things goes, it's important to note that what are Lagrange points? Lagrange points are basically they're very stable points to put things and to keep things at any given time. As you may notice, these points do move along with the orbit. And why is that important? Well, let's say, just hypothetical reasons, I want to put a car outside in front of a store or a building on Earth. I assume once I come back outside, that car is still going to be there. Fine. But in space, is that the case? For the most part, most areas, no, that's definitely not the case. But for the Lagrange points, that is especially the case. That means that you can put a satellite at these points and they should stay stationary to whatever area they're looking at. So for example, if I had light where we have a Lagrange point near America, facing America, this Lagrange point will always, let's actually let this run through and stop that. It will be always facing near America, as you saw here, and L3 is right there. So that's very important to note, because if you want something always faced on somewhere of this side, of the globe, then you need to have it at L1 and so on. Now, the important thing to note is while you can put things at these particular locations and have a safe bet that they're going to be there if you come back, and these are very important for refueling stations, bases, or communication, especially communication, but in other things. The L1, L2, and L3 on this line is not stable. Why is it not stable? Well, the simple fact is what are Lagrange points? Lagrange points are basically where you have one orbiting body, another orbiting body, and the gravitational well working. And basically, it's acting like one person is pulling a rope, another person's pulling a rope, and at this particular point, the energy is the same on both sides, so you're stuck. And the same thing goes with these others. So that's important to note, and eventually things do give a little, and that can shove you to one side or another more so, and that's important to note. However, L4 and L5 are very stable, up to the point that they're almost 100% stable. And around Jupiter, between Jupiter and the Sun, there's actually rocks in L4 and L5. On Earth and the Moon, there is some small debris in L4 and L5. In Earth and Sun, same thing and whatnot. So it's very interesting and very important, because if you want to put, say, a refueling station, put it at L4 or L5, and or a base at L4, L5, and that way you don't have to worry about all that. Now, given that things do collect there and periodically, then you do have to worry about little rocks and whatnot. So L1, L2, and L3 is your best bet to avoid those rocks. And of course, you still might run into a little bit of them. But as far as things goes, what scientists usually do is, let's pull out the sun. Say a satellite's at L1 or L2. The satellite will not be centered on L1. It will actually be around L1s, and it will basically do a orbit around L1, L2, or L3, and this will allow it to stay safe. This is all the Lagrange points, given that we're not talking about the moons and asteroids and whatnot, just the planets and dwarf planets in our system. So these are pretty much it, and there's a lot of spaces so that you can put things and don't have to worry about it. Remember, L4s and L5s, they're stable and things will stay there, relevant to whatever it is that the L4 and L5 is around. Now, it's important to note that L4 and L5 is around 60 degrees from whatever it is. So say, for example, this being the Sun, Earth, whatnot, or the center of a binary system, then what you have here is a center, whatever you're looking at, getting close to. L4 is 60 degrees left, L5 is 60 degrees right, obviously depending on which way you're looking at the thing, if you're looking at it from top up or bottom down. So that's important to note too. Now, as far as why would you care about all of this? And by the way, before I get any deeper, one thing I want to mention real quick is our satellites orbiting Earth, no matter what type, they're also creating Lagrange points. They're not as strong, but still, as you see here, here's a bunch of them in a couple of satellites. So that's also important to note. But why would you want to know this? Let's say here's the sun. We don't know what the other side of the sun looks like. We got telescopes looking from Earth to the sun, but what does the other side of the sun looks like? In a lot of sci-fi novels and whatnot, way back when, before these points were really utilized, They put a evil layer on every side of the sun, and as long as it stays at L3, we won't know what's there. Like, you could build whatever you want, and we don't know. In fact, a lot of people used to even believe that there's planet on either side of this because we couldn't see it. Now, we know the case now that's not, because we've been over there and we've seen the stuff. And we actually have a satellite here at L3, a satellite also at L4 and L5. And basically what they do is the satellite L3 looks at the sun. Since we can't look at this side, we look for activity, being solar flares or disruptions of some type. It will send a signal out. Because it cannot send through the sun, it'll send out to L4 or L5, and the L4 or L5 will send out to the Earth, or L1 then Earth, depending on how exactly it's set up. That's very important. Now, as far as things goes, that means that we can keep an eye out on if the sun's going to act up and spit out some very bad things, which happens time to time. But one of the things that we could use the L4 and L5, because we don't really utilize them. We have two satellites looking at L4 and L5. They're looking at the sun at all given times, and they give you a 3D stereo picture of the sun, and a picture and a video. And it's very, very neat, but as far as things goes, we don't really utilize those areas. If you wanted to, and if you're smart enough, you can put a base there, maybe a launching station, maybe a refueling station, some type of base there, since basically no matter what, you really can launch from here and go to L4 or L5, and you can get what you want, fuel or whatnot, and take off to whatever planet. Same thing goes with the moon and whatnot, and eventually I think we are going to actually utilize that, so that's important to note. Now let's focus this on Earth. Now, as far as this goes, you got the L2, and this is also important to note. If we wanted to, and this is not accurately represented, but if we wanted to, we can actually go out and put a satellite here, and this is what we're doing with the James Webb telescope. We're putting at the L3 or L2, sorry about that, and we are keeping it in the dark because it's always going to be in the dark, always going to be right here, since our Earth is blocking it from the sun. It's able to see all around and stay far enough away where we don't have to worry about the radiation off Earth or the brightness of the sun and whatnot affecting the telescope. Because believe it or not, the Hubble telescope, and I talked to the creators of the Hubble telescope about this to ask them why weren't we using that as spotlight satellites and whatnot. And they said that the telescope lenses are so sensitive to light that any actual light will burn out, even if it's a reflection off sand on Earth. So what they do is they try to find the darkest areas and take pictures of that. And eventually they build up a big enough area because, you know, everything travels through space, and no one besides the sun is static. I mean, even the sun has a little bit of wobble, and I'll get into that in another video. But as far as things goes, they look at the darkest areas. This will allow it to stay in a constant darkness. So that's very important to note. So if you put something at L2, it's always dark. Don't worry about it. Don't worry about the sun keeping it too bright. It's always going to be dark. Now, of course, you're going to have to worry about the asteroids and some other stuff, but that's normal. No matter what point you put at, that is normal. So, So the one thing I want to add, in case if I forgot, is Kerbal Space Program does not have these points. I read around, and I'm pretty sure the developer said it somewhere, but it's just too much for the software to calculate and keep down the memory. Maybe in the future, maybe when they boost it up to 64-bit, but at this time, this particular information is useless when it comes to Kerbal Space Program. But for the real world, this is extremely important, because as I've shown, there is L points even around Earth, and our satellites can be around there, which they are GPS satellites, and they can actually help you out, which most of us have used. So you can develop some pretty cool stuff, and if you wanted to, which eventually we will get to, not in these videos but in humanity, we will be able to actually manipulate the stars and whatnot. And I have no doubt in my mind, because there is rogue stars flying out there, and what rogue stars are is, as you saw, basically by adding something in one place, you can slingshot a star or planets, and it happens to planets too, where it just shoots off and is just flying out in space. And I don't know how often that happens, but we have found quite a few rogue stars and rogue planets. But as far as this goes, we will eventually get to a point where we can manipulate it to make these trails and to do all these fancy things. And one day, one day the sun will run out of fuel, and there's a lot of dangers out there. And one of the solutions that a lot of scientists are coming up with is using a fake sun, making our own sun, or extending the life of our current sun, but having it where we can manipulate where it goes. So instead of picking who lives and who dies by sending everybody to a different solar system to live, because if when the sun blows up, the Earth's gone. But if we can move the entire solar system somewhere to a better star or whatnot, then that solves that problem. And a lot of scientists are working on that. And again, one day we'll be able to actually manipulate all of this stuff. It's just a matter of time, and I'm thinking it's probably going to be probably a good million years, more or less, depending on how things are. It's going to be well out of my lifetime. So anyways, if you got any questions or whatnot, feel free to leave them in the comment section, and that way I can answer as quickly as possible where someone else can. Also, if you have any questions that you want to keep private or whatever, then feel free to email me on YouTube or email me on techreviewsandhelp.com, and I'll try to get back to you as quickly as possible. As far as things goes, I'm actually running out of things to show you and talk about in orbital mechanics, and I can see within 3 to 5 videos we're pretty much going to wrap things up. Might get in some aerodynamics and whatnot, and we might test out some of this stuff, but I think we're going to be done for this shortly. But as far as things goes, if you want me to cover a particular part, especially more detail, let me know, and I will try to do my best in that. It's been Craig Bennett, the founder and owner of Tech Reviews and Help, and I hope you have a great day.